Welcome to this one more lecture on the scattering theory. And in this particular lecture, we will derive or we will see, not the derivation, but we will see what this scattering amplitude is. Right. So before doing that, let me just remind you what we did in the last lecture, because that was the lecture which was very important, the foundation or the starting point of scattering theory. So in the last lecture, we have converted or reduced the two body scattering problem into solving this particular equation, which is the Schrodinger equation for the reduced mass m in the potential V of r in the center of mass, right? So this is the equation from which we will calculate the differential cross section in the center of mass frame, right? And we have derived the expressions for center of mass frame and the differential cross section in the left frame, and that is why we have done all those calculations, because the theoretical calculation, right, we will do in this particular theory is just the solution for the center of mass, and the real experiments we will do are the experiment that are conducting in the left frame. That's why we have to know the relation between these two things, right? So this particular equation, I have told you all these points in the last lecture. So this particular equation number one is representing the scattering of particle of mass m. I have drawn the picture for you in the last lecture from the fixed scattering center that is described by potential V of r, where r is the distance between the center of this particular potential and the particle mu. So this is the conclusion in the of the last lecture, which was the very important lecture. Now what we are going to do is that we are going to assume one more thing. And if you just look at this particular theory, there are so many assumptions: the elastic scattering, the non-relativistic scattering, the spinless particles. One more assumption is that the potential that we have just derived, or let us suppose assumed in the last lecture, is in itself is finite range, is of finite range. What it means is that there is a particular value a beyond which the potential is zero, right? So it is just the influence of this particular potential is in the region for r is smaller than a, and beyond that particular distance, the value of this particular potential will be zero, right? This type of potential we call as the finite range potential, and we are assuming the potential that we are using is also the finite range. Its influence is in certain region, and beyond that certain region, the value of this particular potential is zero, right? And what does that mean is that what it mean is that the particles, the incident particles which were coming from a very far distance from the center of the scattering, so initially they were not influenced by this particular potential, right? So we can say that they are just free particles, right? So they do not have any potential, so they are free particles. So before r is greater than before r is smaller than a, we will consider these incident particle as free particle. Not only that, when there will be some scattering, some influence of this particle potential on these incident particles, and they will scatter in some particular direction, at the detector the influence of this potential we will consider as zero. So even when we are detecting the particles, they are like the free particles, right? So this is what the basic assumptions of the scattering theory, and now we will start solving the scattering problem in more detail. So let me write this particular equation in one more useful form, right? So what you can do, you just have to multiply the whole equation by the reciprocal of this particular term. So it will be like del plus square, which is Laplacian, plus or minus 2 mu over h cross square into p of r into psi of r, which will be equal to minus 2 mu over h cross square into e and psi of r, right? Let this particular term as k naught square or k square, so it is 2 mu over h cross into e is k square, right, where k is the wave number. We will deal with these kind of things what they are physically, but let me write it first. So it will be like Laplacian, and this will be minus k square, and when we will take that particular term on the left hand side, so it will be plus k square, and there will be common this particular term which is psi of r. On the right hand side, you can just take this particular term on the right hand side, and it will be like plus 2 mu over h cross square into v of r into psi of r. So this is an important equation. Let me write it uh, even better in even better way. So if you just assume this particular term as the reduced potential, so let the reduced potential u of r as 2 mu over h cross square into the real potential. So it is just to make this particular equation more simplified, right? So that it will look a little bit nicer. Then this equation will be Laplacian plus k square into psi of r will be u of r into psi of r. This is one of the important equation that we will solve, or we will try to solve this particular equation, because this is the equation which will give us this particular value, right? So this is what the equation is. Now let me move further to get some idea about the solution of this particular equation. And the thing that we are going to do is just completely intuitive, right? So we will use our physical intuition to get some idea, not the exact solution, but some idea about the solution of this particular equation. So what we know is that when the particle, let me draw the figure again. Let us suppose this is just the range of potential, right, A, and these are the incident particles which are coming to this particular potential, and they will scatter in some direction, and there is this detector which will detect the number of particles coming in this particular direction in angle, the solid angle d omega. Now what you know by intuition is that when the incident particles are far away from the range of this particular potential, they are nearly free, or they are just free particles. So incident particles far away from the scattering potential can be considered as free particles, right? Which means the potential at these the influence of this particular potential at this uh, at these incident particles is zero, right? So initially at the incident particle, this particular potential is zero, and that's why this particular equation will be like Laplacian plus k square, right, into psi of r is equal to 0. Why? Because u of r is 0, right, for r is very greater than a, right? So this is very important thing. Now what is much more important than this is when the particles are free, right? So when the particles are free, then we can represent those particles in the form of plane wave. So free particles can be represented as plane wave solutions in quantum mechanics, right? So it is like the incident particle, the wave function for incident particle inc can be written as a, which is the normalization factor, into e to the power iota k naught dot r, right? So this is the plane wave which is representing the free particles, the incident particles coming towards this particular potential. They will interact to this particular potential, and they will again just scatter in some particular direction. So this is the one hint, at least by using some physical intuition, we got about the scattering process. And the hint is that the coming particles are in the form of plane wave, because in the quantum mechanics, if the particles are free particles, then they can be represented as plane wave. Even that is just the only way to represent the free particles in quantum mechanics. You have to represent them as the plane wave, and this is what we did. And this is the plane wave form, right? You must have studied that in your first or second unit. And the plane wave is just some normalization factor into exponential of iota k naught dot into r, vector, where this particular k naught is the wave vector in this incident direction. So it is wave vector. One saying wave vector, even we are considering the particles are coming, because in quantum mechanics particles are just a kind of wave, and we can represent particles in terms of waves, right? So that's why I'm interchanging the word wave and particle. So that incoming particles can be represented, the direction of incoming particles can be represented by the wave vector. So it is just wave vector of incident particle, and this is the incident wave function. That means something is coming with this kind of wave function, and that something interact with this particular potential, and then it scatter in some particular direction. So this is the equation which we were trying to solve. So let me write it there because it is important. So let me just write it for reference. Now the important thing is that when these incoming particles are coming, they are coming as the plane wave, right? They have some particular direction which is represented by k naught, right? K naught vector, which is the wave vector in the direction of incident particles. But after the scattering by this particular potential, right? So they will scatter in all the directions. So it may be that this particle can go in this direction, these particles can go in this direction, they can go in this direction, and there is equal probability, right? So if this scattering potential is symmetric, spherically symmetric, then there is equal probability of scattering these incident particle in all the directions. So what is happening is that it is just the incoming particles will scatter in such a way that it will just look like a spherical wave, right? So it will look like a spherical wave coming outward. So this is one more intuitive thing that we can think, that the particles are coming from a particular direction, but after scattering they have equal probability of scattering in any direction, so that there is some kind of spherical wave of probability, you can say, coming out of this scattering center, and it is just only spherical when the potential, which is the scatterer, is spherically symmetric in itself, right? So one more intuition or intuitive thing we got is that after scattering by the potential V of R, right? And if V of R is spherically symmetric, so is spherically symmetric, then the scattered particle can be represented by the spherical wave, right? Then the scattered particles can be represented by the spherical wave, right? With, we can say, dying amplitude. So what it means is that the plane wave are coming, and after scattering there is this outward spherical wave. And in quantum mechanics or mathematically, we can let us suppose the scattering wave are psi sc, right? So they can mathematically they can be written as a to the power iota k dot r over r, right? So this particular thing which is spherical wave, and this 1 over r will r is just representing that the amplitude of the spherical wave is just dying when it is moving outward, right? So this is the form of outward going particle. So you can say this is the form of wave function of the scattered particle from this particular spherically symmetric potential, right? But it is just when the potential, the scatter is spherically symmetric. But in general, it is not the guarantee that it will always be the spherical symmetric potential. It may be like the potential is like this, and therefore the scattering in different angles or different direction will be different. So the amplitude of the scattered particles, this scattered outgoing wave, will also depend on the direction in which they are scattering, right? So in general, the scatterer or the scattering potential is not spherically symmetric, right? And it depends on the direction theta and phi. Hence we have to include one function which is just the function of theta and phi in this particular scattered wave, right? So we have to write this scattered wave as some function which is just the function of theta and phi times this particular value, which is iota k vector dot r vector over r, and this is the wave function for the scattered particle, and this is the general wave function because this has theta and phi and it has r. So this is representing the spherical wave coming out of this particular symmetric potential. But if the potential is not symmetric, then there is this particular function which will represent the influence of the scatterer in different directions, right? You can add one more constant, the normalized constant, so that the overall function is normalized. So what is the conclusion of this particular talk is that in the scattering phenomena or scattering processes, the incoming particles are free particles which are in the form of plane wave, but after scattering they will be some kind of spherically symmetric, not the spherical symmetric, but they are just scattering out of this particular potential, right? And the scattered wave will always be in this particular form, right? So the incoming or incident particles are plane waves which are in this particular form, which is k naught, and here k naught is the incident direction, but in this particular expression there is this k, not the k naught, which is representing any direction, right? So if you are representing any direction, it is just k in any of the direction, but k naught is fixed, right? Because incident particle once released are fixed to, or bound to move in some particular direction, let us suppose in z direction, but the particle after scattering they are free to move in any of the direction. That's why it is a constant, it is just a variable, right? So this is the plane wave, or it is incident or incoming waves or particles, let me write. And what we found by intuition, this scattered wave will always be in this particular form, theta and phi, and there is this which is iota k dot r over r. This is the scattered wave, and in this scattered wave, this particular quantity which is f of theta and phi, this quantity, right, where f of theta and phi is called the scattering amplitude. Scattering amplitude. So this is the quantity which is called the scattering amplitude. Scattering amplitude is this particular function. So how you can define this scattering amplitude? So you can define it as scattering amplitude, which is just this function phi of theta, f of theta and phi. So this is a function, a mathematical function of direction theta and phi, which will give us the amplitude or probability amplitude of scattering particles in some particular direction after scattering by the potential in center of mass frame. So this is the rough definition of scattering amplitude, and scattering amplitude is just this particular quantity which will give us or which will help us to get the scattered wave function, because this is the function which will help us to calculate the number of scattered particle in this particular direction, which is the differential cross section, and that is the quantity that we are looking for. So now you can just see how we are connecting things, right? So there are so many assumptions, and out of those assumptions, this is the important definition which we got, and this is the way to think about the scattering processes, right? In the scattering processes, the incoming particles are assumed to be the plane wave because they are free particles, but after scattering, the wave is scattering out of this particular potential, which will always be in this particular form, right? So if the potential is just the spherical symmetric potential, then there will be just this particular term, and if the scattering potential is not symmetric, so in general there will be this particular function which will determine this probability amplitude in this particular direction, right? And this particular function, which is function of theta and phi, which means the function of direction of the particle or of the detector, which is detecting the scattered particle, and this mathematical function is called scattering amplitude. Why this is very important quantity? So in the next lecture, we will see why this particular quantity is very important, and we will derive a relation, right, in between the differential cross section and this particular quantity, the scattering amplitude. So let me write it for you. The relation that we will get is this differential cross section is always be the square of mod of this particular function, right? So the most important relation uh, in the lectures so far I have delivered. So this is the relation that we will calculate in the next lecture, but it is just to show why this particular quantity is very important for us. So it is important because if you have this particular quantity mathematically, then you can just take the mode and have the square of that particular mode. You will get the differential cross section, and this is the number that we are looking for in this scattering experiment. That's why this scattering amplitude quantity is very important, and this is it in this particular lecture. And in the next lecture, we will derive this particular relation in between the differential cross section and scattering amplitude. So thank you.